Tonight we open 3 case files at once. 3 travelers that broke the silence of interstellar space and slipped through our solar system like whispered confidences. These are messengers from other star systems. One that arrived furtively and puzzled everyone. Another that announced itself with classical cometary theatrics. And a recent high-speed guest that our modern skywatchers caught early enough to learn more than ever before. Each visitor brings different evidence, though motion, light, chemistry, and together they begin to sketch a new catalog of what interstellar material truly looks like. The first visitor, an unsettling oddity picture. The first arrival, discovered in October 2017, it presented as a lone point of light with a hyperbolic trajectory, a clear sign it came from outside our sun's family. At first glance, it was mute. No bright coma, no obvious tail, yet the way its light varied suggested a complex rotation and a peculiar shape. The motion, when tracked carefully, betrayed a secret, a small non-gravitational acceleration nudging it away from a pure Keplerian path. That tiny, measurable push, while only amounting to tens of meters per second over months, was a scientific bombshell. Was the push caused by hidden comet-like jets? Or could sunlight itself act like a breeze on a very thin surface, producing radiation pressure? Teams around the world modeled and remodeled the orbit, and the debate became a defining moment for modern small-body science. Why does a small acceleration matter? Because it carries fingerprints of physical processes. If outgassing were responsible, then the object must be venting volatile compounds, gases that escape when warmed, even if telescopes failed to catch the usual spectral lines. If radiation pressure is the cause, the object must have an extreme area-to-mass ratio. Imagine a paper-thin, lightweight structure pushed by sunlight. Both interpretations strain conventional expectations and force us to consider a wider family of natural bodies and to confront questions about detection limits and hidden physics. The second visitor, a comet that sang its chemistry, now shift the scene to late 2019. A second interstellar traveler appeared that behaved very much like a comet. A coma, a dust-laden tail, and spectroscopic signatures that telescopes could parse into chemical ratios. What shocked observers was not the presence of ices, but their relative amounts. Multiple studies measured carbon monoxide at abundances far higher than typical solar system comets, in some cases exceeding water by factors not seen in our neighborhood. This chemical fingerprint shouted a story of formation in an extremely cold environment, perhaps in the distant outskirts of another system, where CO ice could remain stable long after water has sublimated. Those measurements gave us our first real peek into the volatile inventory of a different protoplanetary disk. What does that mean for planetary science? Simple. Planetary systems are chemically diverse. This visitor carried volatiles that suggest parent systems can lock away different proportions of ices and organics. From an astrobiological perspective, that's profound. The delivery of water and complex organics to young worlds is thought to seed habitability. Knowing that other systems package volatiles differently means the galaxy's recipe book for life may be broader or stranger than we once imagined. The third visitor, a modern detection in a new era. Fast forward to 2025. The third confirmed interstellar object was flagged by wide-field surveillance and confirmed to be on a very hyperbolic orbit with high excess velocity, meaning its origin is unmistakably interstellar. What made this arrival different wasn't only its trajectory, but the era that caught it. Modern survey networks, higher cadence observations, and a global community poised for fast follow-up. telescopes across wavelengths mobilized quickly, capturing better photometry, early spectral snapshots, and evolving coma structure as it warmed while approaching the sun. That early multi-instrument response is transforming how much we can learn from each visitor. Early detection matters because it multiplies the observational windows, pre-perihelion, perihelion, and the inbound versus outbound asymmetries. It allows scientists to measure light curves before thermal effects dominate, to search for volatile outgassing at larger solar distances, and to track morphological changes as heat alters the surface. In short, catching an interstellar messenger early converts a fleeting cameo into a sustained study. Trajectories, speeds, and origins. Forensic kinematics. Trajectories are our first clues to origin. The velocity at infinity, the speed an object has far from the sun, gives a lower bound on the energy needed to escape its parent system, and its incoming direction hints at potential stellar neighborhoods. But most interstellar objects show approach vectors that are effectively random at galactic scales. That randomness tells us something important. Ejection mechanisms are common and chaotic. Planets throw material around. Binary stars and passing neighbors stir disks. Collisions and gravitational scattering are routine in a galaxy that has existed for billions of years. Comparing the three travelers reveals a spectrum, one with non-gravitational quirks, one with volatile-rich chemistry, and one with high-velocity, well-observed passage. These differences suggest distinct ejection histories. Violent collisions, gentle outer disk liberation, and planetary scattering can each preferentially produce different kinds of interstellar debris. What are these objects really? They are physical pages torn from other planetary systems, records of formation, chemistry, and dynamics written in ice and rock. They tell us that planetary systems eject material across a spectrum of types, and that the galaxy's debris field is both variegated and informative. Each visitor narrows hypotheses, refines models, and reveals new questions about how materials were mixed in disks, about how collisions and planet scattering sculpt populations, and ultimately about how common the building blocks of life might be across the Milky Way. If you want to follow the next arrival and the emergent story it will add to this unfolding cosmic library, subscribe to Discovering the Unknown. We will be there to unpack the data, interrogate the models, and narrate the discovery with the clarity and cinematic scope you expect.